Select the major product of the following reaction. So if we take a look at our reaction conditions, we are starting with an alkene, and specifically we are starting with an alkene that is in the trans orientation. That is to say, the two alkyl groups on the alkene are pointing in the opposite directions. So this is a trans alkene. And then we need to look at the reagent that we are reacting this with. So we are reacting this with MCPBA, and so we're going to need to remember what MCPBA is. So let me draw the reagent up here. So this is the structure of MCPBA. So it is a peroxy acid. It has a benzene ring and it has a chlorine. And specifically that chlorine is 3 carbons away from the peroxy acid. We call that meta. So this is meta chloro, because it is a chloro that is meta, peroxy benzoic acid. And so that is where the acronym MCPBA is coming from. All right, so the important part for us in this reaction is really the peroxy acid part. So I'm going to draw just a generic peroxy acid, and we're going to take a look at how they interact with alkenes. So we're going to draw ourselves just a quick little model reaction. So I'm just going to draw an alkene up here, and I'm going to line up the peroxybenzoic acid, how it's going to react with the alkene. So this oxygen right here, the one that's attached to the hydrogen, is electron deficient. So it is electrophilic, and we know by now that alkenes are nucleophilic. So I'm going to line up this oxygen with the alkene. So bear with me just as I draw this structure. So I've got my peroxide portion and the carbonyl, and I'm just going to use an R group. In this case, it is the benzene with the chlorine, but we could see other examples of peroxy acids. All right, so this oxygen here is electrophilic, so the alkene is going to react with it, and that's going to set off as a series of reaction steps of arrows. So we are going to push these arrows into here, so we're forming a carbonyl. And we're going to take the pi electrons from the previous carbonyl and grab the hydrogen. So that means that we are bonding this hydrogen to this oxygen. And we're going to use the electrons from the oxygen-hydrogen bond to come back around and bond to the alkene. So let's see if we can follow what those arrows are doing. So we are overall transferring this oxygen to be bound to both carbon atoms of the alkene. So we are making a 3-membered ring that has an oxygen, and we would still have whatever groups were bound to the alkene carbons. So a structure like this is called an epoxide. So that is a 3-membered ring cyclic ether. And if we follow the arrows here, the peroxy acid is just becoming a carboxylic acid. So we're going to have a carbonyl bound to a carbon that is going to have a single bond oxygen, single bond hydrogen. So we're also forming a carboxylic acid. All right, and it is the epoxide portion that we are going to focus on. So we can see we're going to be considering one of these 2 epoxides as our product. And we want to pay attention to the stereochemistry. So we started with a transalkene. This reaction step here, this is where the new bonds are forming. This is a concerted reaction step. So it is a concerted reaction. We can see it's taking place all in one step. There is no time for this bond to rotate, for the groups to move around. So any stereochemistry that you had present in your alkene will still be present in the epoxide. So since we started from a transalkene, our major product should be the trans epoxide. So whatever your alkene is, you're going to pay attention to where the groups are relative to each other and make sure that they are still in the same positions when you're drawing your epoxide product.